Okay, now I'd like to talk about mathematically how do you actually send rays out through pixels. So how do you figure out what their direction vectors are? Now the position vector of every ray is the same. So all the rays will end up coming out of the eye. So the eye is like this focal point. But let's look at the extremes of where the rays can go. So let's say that this is sort of the furthest to the left that I can go here, and this is the furthest to the right that I can go. So it's symmetric, as many things are in human perception. And what we do is we say this angle here from one end to the other, that is called the field of view. So I'll say f of v. Okay, so these are the extremities of what I can see. And we'll make them a hard cutoff here. Of course, there's peripheral vision, and it's kind of on a continuum, but we're going to make this a hard cutoff. And so the field of view is a parameter that kind of orients, or that says how wide we can look in. But we also need some stuff to orient us. So we need to know where is the eye looking. And for that, we need actually two things. We need a vector that says what is the direction towards. So I'm getting a little sloppy here. These are vectors, towards and p0. So p0 is the position of the eye. Towards is a vector. We actually need another vector too, which is a vector that says what is the direction to the right of the eye. So this is the right vector. Okay, so with towards, right, and the field of view, we have enough parameters to figure out where all the rays should go in between these two extremities. But first I want to make just a quick observation. Let's try to figure out, well, what is the ratio between the component of the extreme direction vector here in the towards direction versus the component in the right direction. Okay, so it's this picture here. I want to know what's the ratio of the length of this vector to this vector. So now we just got to go back to some trig and notice, well, okay, this is a right triangle, since right and towards are perpendicular to each other. And it also happens to, since I said this is symmetric, this is half of this full field of view, everything to the right side. We have a congruent triangle on the other side. But focusing on this one, what we see is the length of this vector in the right direction. So we'll say the length of right is actually equal to, well, let's say it this way. This angle here is the field of view over 2, right? Since I divided this in half. So what I'll say is the tangent of field of view over 2, so the trigonometric tangent, is equal to the length of the component in the right direction over the length of the component in the towards direction at this extremity here. Okay, so the ray that's going all the way down. So remember that the tangent is opposite over adjacent. So the opposite here is the vector in the right direction, the adjacent is this vector in the towards direction. So if I rearrange this, what I get is that the magnitude of the right vector, the length of the right vector, is equal to the towards vector times the tangent of the field of view over 2. Okay, and if these, we're going to say these are unit vectors, so we might as well say that. So what we say is the furthest along I can be along right is just 1 times the tangent. So, okay, so tangent of field of view over 2 is the furthest I can be in the right direction. So I'll set up a unit vector in the towards direction. So my final direction vector is going to be towards assuming towards is a unit vector, plus right vector times tangent of field of view over 2. Okay, so that's going to be this vector here. And you know, the one at the other side would be towards minus right times tangent of field of view over 2. So that would be this vector up here. But what about rays in between? So what about this ray? So I'm going to send this ray out somewhere. Okay, so this ray will go through a pixel. And so that pixel will actually determine the direction of the ray. So you can do that the other way around and say, okay, if I'm going through this pixel, which direction would that ray be? So let's go back and remember that we're actually going to do a real-time ray tracer using shaders. So we'll use the shader coordinate system. And right now I'm just focused on towards and right. So, you know, this is the x-axis here and this is the y-axis. So right is on the x-axis. So let's say I'm just focused on this line for a second. I'll worry about up, down in a moment. But so let's say that it looks like I probably picked this pixel around here. I'm this far to the right of center here. And so I'm casting a ray through this pixel, and this is the furthest extremity. What I can say is, well, I know that when you're at 1, the vector is going to be towards plus right times tan of field of view over 2. But actually, for here, we can just say, for a general pixel anywhere from right to left, it's going to be x. It's going to be right times x times tangent of field of view over 2, where x is some number between -1 and 1. So if I'm at 1, it's as far as I can be. It has the most right component it possibly can. If I'm at 0, it has no right component. It's fully in towards. And if I start to move negative to the left, you'll see that it actually subtracts off the right vector. Okay, so this is how you can determine the direction vector. So it's the tangent of the field of view over 2. And actually, to do this in 3D, let's say that we pick a general point that has the coordinate x comma y. So now I'm not just on the x-axis, but I'm going up and y. So I'm really trying to cast out rays through all these pixels. Well, by the same argument, you can say there's also a field of view in the y direction, not just in the x direction. And the picture is exactly the same. So I'll say that this happens to be my field of view in the x direction. But there's also a field of view in the y direction. And in that case, I have a vector pointing up. And you can obtain that vector by, if we look at the right-hand rule, that should be the right vector cross the towards vector. So we'll say up equals right cross towards. And if we do that, and so assuming these are both unit vectors, then what we can write is the full equation for the direction vector of your ray going through a general pixel here is towards plus right times x times tan field of view over 2. Sorry, tan of field of view in x over 2 plus up times y times tan of the field of view in y over 2. Okay, so this is the equation you need to do ray casting. So this determines a direction of a ray that I'm shooting from my eye through a particular pixel. By the way, we call this the viewing plane. So where the pixels go through here, that's called the viewing plane. So I'm setting this viewing plane here, and I'm shooting pixels through it. And then all the rays, I'm shooting rays through those pixels, and all the rays come out of the eye. Okay. Now I just want to take a moment to look and to understand the implications that this geometry has on how we see things. So if I go back here, there's a couple things I can mess around with here. Notice now that there's a field of view in x and a field of view in y. If I make the field of view in x larger, you see I can see more, right? So the field of view in x started out around 1.4 radians, but as I make it bigger, I can see more and more, right? And the limit of this actually is as I make the field of view closer and closer to 180 degrees, so pi, I could actually see infinitely in all directions. Because that's like saying I can see all the way out here. That covers everything in front of me. So you see when it starts to, and this is a property of the tangent too. The tangent grows very, very quickly as you grow towards pi. So pi over 2 is, tangent grows very quickly as you move towards pi over 2. And so we're moving towards pi, but we have the field of view over 2. So what you see is, the component of the right vector approaches infinity with respect to the towards vector. Okay. But I can also mess with the field of view in y and do the same thing. So now I'm seeing a lot more in the y direction. And this looks really weird. We don't really see it this way. We have a much more symmetric field of view across both those axes. Okay. But another thing I want to point out here, so it's not just the field of view itself that's interesting, but even the fact that we're doing perspective rendering at all, we see some interesting things. So for example, if I were to go, let's say, move myself over here, if I look at just the amount of pixels that this ellipsoid takes up versus the amount of pixels that the dino takes up, it looks like this is way bigger than the dino, right? But that's only because I'm seeing from a perspective in this way. So what we notice is, from this sort of perspective thing, that objects that are closer to me appear a lot bigger than objects that are further away. And this is something you probably take for granted. But if I look at, so let's say this is my eye, and so this ray, if I sent this ray out here, this would cover the edge of the sphere there, and if I sent the ray out here, it would cover the edge of the sphere there. But what you notice is, in order for that to take up the same amount of area in my viewing, it would have to be much bigger further away, right? So this sphere and this sphere would look like they're the same size because they end up projecting to the same amount of pixels here. So that's one weird thing that happens with perspective rendering. So that's why things that are far away look so small. And if you blink one eye and blink the other eye, and you put your finger in front of it, if you move your finger a little further, it doesn't move as much as when you have it close to you. So that's one of the things we get from perspective viewing. And it's just the fact that we focus light rays this way onto our eye. And so we end up seeing that way. But one thing you can do, which is a little bit wild, is you can have these orthographic views. What that means is, I'm not going to do this thing with the weird trig, the tangent. What I'm going to say is, if you are trying to fill in a pixel here on the viewing plane, so if you're trying to fill in a pixel at this location, well, I'm just going to take, it's not going to be the tangent, I'm just going to take the towards plus x times right. So here's my towards again. And then I'm x over. And so then I'll have my right vector like this. And I'll just say, instead of towards plus tangent of field of view over 2, I'll say just towards plus x times right. Okay, so this is called orthographic. And I'm going to show you a video on the next page, just a real quick video of what that looks like.